Let's solve some rational equations. Our general strategy is to try to clear the denominators from any rational expression. In this first example, things are pretty straightforward because the only denominator is x minus 3. So I can multiply both sides of the equation by that factor. And I'm going to write this out carefully. This is going to become x squared minus 1 times x minus 3 over x minus 3 equals 8 times x minus 3 over x minus 3. And we wouldn't always need to write it out so carefully, but I just wanted to be clear. This is distributing to both sides and then canceling with the two denominators. So my equation becomes the simpler quadratic equation, x squared minus 1 equals 8. And we can solve that by adding 1 to both sides to get x squared equals 9. And then, of course, we can take the square root. Don't forget, when we do this, we need to do a plus minus next to the number, and we get x equals 3 or x equals negative 3 as two possible solutions. So I really want to highlight these are possible solutions. These are the two values that could work. But if you think back to our conversations earlier about restricted values, x can't equal 3. So 3 is not actually a solution. Positive 3 is called an extraneous solution. It's something that's created by the process that we use to solve the equation, but it doesn't actually satisfy the original equation. So it should work out that negative 3 satisfies the equation. To make sure, we can check, as we can do with any equation, by plugging that value back in. If I do, I get 9 minus 1 over negative 3 minus 3 on the right-hand side, which is, of course, 8 over negative 6. And on the left-hand side, we already have an 8 in the numerator. If I plug in negative 3, I get the same thing, 8 over negative 6, which, of course, simplifies to negative 4/3, but it's the same in any case, right? So we get the same value on both sides. So negative 3 is a solution. Positive 3 came out of our process, but it's not actually a solution. So let's look at a second example. This time I want to make sure I factor the denominator. I get c minus 2 and c plus 2. And thankfully, those turn out to be the other factors in the other denominators. So to cancel out those denominators and create a simpler equation, I can multiply by c minus 2 times c plus 2. And this time I'm not going to write everything out quite so carefully. Both of those factors are canceled out by the c squared minus 4. So we just get a 3c from that first term. Only the c minus 2 is canceled out in the next term, so I'm left with c plus 2. And on the other side, of course, the c plus 2 cancels out, and I'm left with 2 times c minus 2. So this time we have a linear equation to solve. So I can just gather together the like terms. 4c plus 2 equals 2c minus 4 if I distribute that 2 to the two terms in the parenthesis. Subtracting 2c from both sides, and also subtracting 2 from both sides, gives me 2c equals negative 6, so c equals negative 3. And now I can look back at my original expression to think about excluded values. The value of c can't be 2 or negative 2. That's not what we found as our possible solution. So this should work out as a solution, but of course we can check by plugging it back in. If I plug negative 3 back into the left-hand side, I get negative 9 over 9 minus 4 plus 1 over negative 3 minus 2. Well, this becomes negative 9 over 5 And then with a little bit of simplification, I can see this is negative 1 over 5. 1 over negative 5 is the same as negative 1 over positive 5. So I have negative 10 over 5, which is equal to negative 2. So that's on the left-hand side. On the right-hand side, I have just 2 over negative 3 plus 2, which is 2 over negative 1, which equals negative 2. So it works out. We get the same thing on both sides if we plug negative 3 back into that equation. So let me just take a moment to point out the general strategy here. We start by factoring any denominators to find what we need to multiply by to clear all of the denominators. And then we do that. We will either get, hopefully, a linear equation or a quadratic equation, something that we can solve with other techniques. Once we find those solutions, we want to be careful to think of these as possible solutions for a moment, because there might be restrictions to the domain, and if that is among those restrictions, we need to exclude it. We call that an extraneous solution when we find a solution that doesn't actually work in the original equation. So I want to think of this as a possible solution until I check it in those two ways. I want to see whether it's among the restricted values. If it's not, we can also check by actually plugging it back into the original equation and making sure that the two sides of the equation agree. Once we do that, we can say, this is an actual solution. I can get rid of that provisional idea of it being a possible solution, and we're good to go. We found our solution to the equation.